Okay, it's 6 p.m. I think I can start. People can join in the middle as well. I hope I am audible and you can see my screen, my presentation. I
Good
will.
evening.
Uh,
Yes.
okay, thank you. Thank you for the confirmation. So, have you attended like previous live session or is this your first live session?
This is my first time. I'm in teaching profession.
Okay,
I'd
okay.
like to make this as a faculty development program.
Oh, okay,
I have a background of research in MEMS at IIT Mumbai. So
so
during that course, I have inclination to this topic. I'm from instrumentation engineering. So I just had uh, desire in mind because I won't commit here and there nowadays. I'm about to retire after 2 years. I'm teaching this course, so I just thought to interact. But I hardly get a chance today. I came earlier from my job location, so I want to participate. I would see other recordings which are previously available. So I'm a registered candidate for this as a faculty development program.
okay.
Thank you.
Okay, ma'am. Actually, the class timing is like 6 to 8 p.m. So the live sessions they have kept mainly on weekends or on Monday or Tuesday because after the course contents are released, so that is why. So these timings are given by the NPTL team so that people can join even if someone is working, something like that. So that is why the timing is kept like from 6 to 8. So I will introduce myself first. So I am Ananya. I am a PhD student in the Department of Electrical Engineering, IIT Kanpur. So my specialization is microelectronics and VLSI. And so I am the TA for this live session for the course Sensors and Actuators. And currently I'm not working on sensors. I did in my MTech thesis during my MTech thesis. And right now, so I work in my fabrication lab. So we work in fabrication of like different semiconductor devices, surfaces, structure. Okay, and I am doing this live session or this TA shift as a part of my PMRF TA program. I have to complete few hours of TA duty for PMRF, and for that I'm doing this live sessions. Yeah. So this is week 10. Uh,
Thank you, Ananya, for your introduction. I'm Rajshri. I was PhD student in 98 in IIT
okay.
Mumbai, but due to fabrication facilities, I had enough time to completely do the microfabrication, all IC technology. So I worked in those labs.
Okay.
After my graduation, after my PhD, then the facilities they're developed as Center of Excellence in Nanotechnology. And I visited ISC Bangalore 2 3 times because I was the NP MAST National Program on Micro and Smart Structures. I was coordinator from my college.
Okay.
So I attended several meetings and had interaction with KJ Vinoy, now Kant Bhatt sir, so many from ISC Bangalore. So this is
So
nice to
we
meet you because we are only two on two sides. So I just thought of
uh,
talking to you. You can start. Thanks. Thanks a lot.
thank you, ma'am. I have little bit of experience of microfabrication, and as I am going through this course, I also watch the lecture videos and try to incorporate whatever I learned, and the similar questions. Those are like given in the assignments, so I try to give those questions here and practice. So few students join normally sometimes after the session. I normally start after 5-10 minutes because people keep joining, and some people watch in YouTube as well. The main idea for live sessions is to give a brief idea about the topics those were covered, and then we discuss about few problems. This course does not have numerical problems, that many numerical problems, but in other NPTEL courses we have numerical problems. So in this live session, I normally solve those numerical problems, and for this course I gave some theoretical question and sometimes one or two numerical question which is relevant to the topics. Okay. Let's start the session. I will not. Okay, yeah. So I can't see the whole screen properly, so I will be in the presentation mode most of the time. The topics those were covered in this week. So this is week 10. We have like two more two more classes of live session, and I might take one summary session before the exam as well, covering all the topics, so that I can give you a brief idea about the whole course, maybe in 1 or 2 hours. In this week, the topics those were discussed. First topic was micro cantilever for breast cancer analysis. The topics those were briefly discussed in this lecture video was that uh, if a if breast cancer, so the tissue is cancerous, the breast cancer can be detected using some properties of the tissue, and we can use micro or nano sensors for that detection. We have like other conventional techniques like mammography and biopsy for cancer analysis, but like microsensors can also help in detection to precisely detect, because there are certain biomarkers for detection of breast cancer, and many times those biomarkers are not even present even the tissue is cancerous. We using this kind of like combining sensing technology along with the conventional techniques, we can reduce the number of false negative detection. Okay, so it's my cursor. Okay. If a tissue is cancerous, some property of the tissue changes. Okay. Which can be detected using a microsensor. Now the sensing mechanism can be different. It can be based on microcantilever, which uses a piezoresistive sensor as discussed in the class, or it can be based on some electrical properties like impedance change, and for that we will use an impedance measurement sensor like an interdigitate electrode made on a silicon or any other substrate. So what are the properties that we look for? It can be mechanical properties, such as elasticity. It can be electrical properties, so impedance of the tissue. So now normal tissue and cancerous tissue will have different impedance. And can be thermal properties. Okay, say heat transfer properties. Now, this sensor-based analysis, sensor-based cancer analysis may not be like sufficient, like on its own. So we have to combine it with other techniques. But overall, it can be a like great help in determining the cases which are like false negative. Okay. Now there are different types of based breast cancer. So that was discussed in the class. I'm just giving you the names here. Uh, I'm not working in this area, so I don't know much in the details of different types of breast cancer. But that can be small questions in the assignment as in the exam as well. So that is why I'm giving you the names here, and this will be for your reference. I will share these notes on every week. So what are the different types of breast cancer? So first one is ductal, lobular. If next one is mixed. This is depending on the location, and so these two are mainly depending on the location of the cancer tissue, like where the cancer tissue is present. Next is inflammatory. Now if you are working in this area, or if you are interested to know more about it, like how different types of breast cancer can be detected and what are the difference, then you can look for it. I'm just giving you the name as discussed in the lecture videos. Now what are the different conventional techniques for breast cancer analysis? It can One is mammography, and another one is biopsy. So in these techniques in biopsy, so what they try to do, they try to find three different biomarkers. Those are for breast cancer, but there are a certain number of, I don't remember the percentage, that was discussed in the lecture video, that some percentage of breast cancer actually gives false negative report in biopsy. So these three biomarkers are not present. So in that case, we can use other techniques, and another one technique that is also used is mammography. That is also not useful in many cases if the tissue is very dense. In that case, the technique cannot be used. And some of the techniques are invasive, and as well as they require some kind of radiation, because in mammography X-ray is used, so that can be damaging. So that is why we are trying for other alternatives like microsensors. Now this kind of work, actually if someone is working in sensors, especially in biological sensors, then uh, like that needs a lot of trial and error and lot of analysis, because we want to precisely detect if there is a change in tissue properties, and that change can be very small. So that is where it comes the sensitivity and other sensor characteristics that we have discussed in previous weeks. So the main point here, why we are working in, why many research groups are working in sensors for cancer cell detection, cancer tissue detection, that is because the gold standard for detection of cancer, the conventional methods, which are may not be always true. Okay. Now the sensor that can be used for breast cancer analysis that was discussed in the class was a piezo resistive sensor that has a cantilever, micro cantilever, and this is the fabrication flow for the discussed sensor. Okay, so I will briefly discuss it. Basically, the structure is like it has a piezo resistive material that uh, if a pressure is applied due to if a result because of the change in the pressure, because of the different elasticity of the tissue, the pressure applied to the piezoresistive sensor will be different, and that will result a change in the resistance of the piezoresistive material. So it has like three components. One is the piezoresistive sensor. There will be contact pads, and it is placed on a cantilever, and there will be a tip that is of SU weight, so that is to apply pressure on the tissue, and this cantilever will bend. So basically we will not see the fabrication flow for this kind of a sensor. So this sensor was discussed, I think this was made in his group, Professor Pandya's group. So they have this kind of a structure. It may not be exactly same for, it can be different. The fabrication flow will be different for a different kind of sensor. But this is just an example. So for this work, they have used a SOI wafer. So this is silicon on insulator. So this is silicon. You can see the colors here, and then this green layer is SiO2, and on top of it this is again silicon. Now first what they did, they did a deposition of uh, SiO2 here, and first they are making this piezoresistive sensor. So boron doped silicon is a piezoresistive material, so that is why they have made an opening using photolithography on this SiO2 layer for boron doping. So this yellow part is a boron resistor. Basically they did the doping in this window, and after that so now we have the boron resistor that will act like a piezoresistive material. And what we need next is we need connection from this piezoresistive material. Now we cannot directly put a metal line or metal connector from this boron doped silicon layer, this boron resistor, because that will not give us an ohmic contact. So that is why they made this boron contact, so so that we can get like a good contact from this resistor. So this material they have not like exactly defined what it is, but this material should have electrical properties so that it gives a ohmic contact with the boron resistor. After making the contact, they are making this connections for the piezoresistive sensor. So till now we have this one step of lithography. So this is one step of photolithography. We have discussed about photolithography in details in earlier classes. Next they did doping, and then did another photolithography step here for the contact, and then they probably did another lithography here to make the gold lines, the connections. Okay, after that now we have the piezoresistive sensor. Now we will make the cantilever. So for that they made this pattern layer of silicon nitride, you can see here. So for this also we need another lithography, deposition and etching, all those tips we have discussed, like how we can make patterns on different substrates in earlier weeks. So that's how they make this silicon nitride patterns on top of here. Okay, now they will make the cantilever, and that can be done. Okay, so before that they have made this SU weight tip to press the tissue. Okay, so that will need another step of lithography, and once the tip is made, they are making they are doing another step of lithography for this back opening so that we can go for bulk etching. So this is the sixth lithography step, and then they did the etching. So you can see the number of steps, how many number of steps are required for this fabrication of this sensor. So this is a fairly complex structure, and we have like multiple levels of photolithography. So after the first step of lithography, we can just roughly do the first step of lithography, but from the second step onwards we have to do proper alignment, because we are making some structure on top of one another structure. So this contact should be here, not somewhere here. Okay, so there the second mask in the photolithography should be aligned in such a way that we get the contact with the boron resistor, not somewhere else. And similarly for other cases as well. And in this case, for this last step of lithography, we also need front to back alignment, because we are doing the lithography at the back side. Okay, and in its photolithography steps, we have all these different steps of photolithography and all the steps of deposition and then etching. Okay, so this is briefly about how we can make a micro cantilever based sensor for breast cancer analysis, as discussed in the class. So I'll take a pause. Is there any question?
Ma'am,
Yes.
what is SU8 here?
SU8, so this is a negative photoresist. We have discussed about the SU8 earlier. So this is like a tip of the cantilever to put pressure on the tissue. So we have discussed about SU8. So how so SU8 is a negative photoresist, if you remember. So it becomes hard when it is exposed to UV light, and we use SU8 to make walls of SU8. So suppose we have a biological sample that is kind of liquid, say liquidy consistency. To hold this on top of our sensor, we make a SU8 wall. So maybe that is because of the biocompatibility, and SU8 we often use in with silicon, because like in silicon photolithography process. So SU8 is well known. We know how to use SU8 with like all the parameters of photolithography is defined, and it is transparent. That is also one advantage. So maybe that is why they are using SU8. Why they are selecting particularly SU8 for this purpose, that I'm not exactly sure, but that is for the tip of the cantilever, and that is to put pressure. Your tissue will be here. So this tip will press the tissue and will give that pressure feedback to this piezoresistive sensor. Okay. Okay, I hope that is okay. I will go to the next slide. So the next topic was photoresist coating. So we have discussed about photoresist coating in last few, I don't remember in which week, but we discussed about photoresist coating while we are discussing photolithography process. Okay, so this is the image of a spin coater, using which we will do we normally do like photoresist coating. We clean our wafer or substrate. There may be some patterns order position before doing like photoresist coating as well. So we place our wafer or our sample here. So this is the chuck. So we connect it to a vacuum pump. Photoresist coater, the spin coater that was shown to you in the lecture video may be a little bit different, but the mechanism is similar. So there will be a vacuum pump connected to it, and this chuck will hold the wafer, okay, because we are connecting it to a vacuum pump. uh, so the sample will be in the chuck, like on the chuck, so it will be kept, it will be hold tightly. And then what we do, we draw few, we put few drops of photoresist on top of our wafer depending on the size of our wafer. And then uh, we will spin coat the wafer using that photoresist, and we will set our spin coating speed. So we will set the rpm and timing, say 60 seconds. So this is the timing. And we will spin coat the photoresist on our wafer. Now the thickness of the photoresist, that is important, because other parameters of photolithography like exposure time, development time, and if you are going for lift off of some material after photolithographies, and all those things will depend upon the thickness of the photoresist, and we can control the thickness by playing around with the rpm and the timing. And the viscosity of, based on the rpm and the timing, and based on the viscosity of the photoresist, will get a certain thickness of photoresist on top of our wafer. And after that, so this is like the first step, and after that we will go for soft baking and exposure and alignment, all those steps of photolithography. Now, as I mentioned earlier, that we have to be careful with certain things while doing photoresist coating. This is the first step. So, as I mentioned earlier, also there are multiple steps in a photolithography process, and if we make mistake in one of these, then we will not get the desired result at the end. So, first problem that may occur is that there may be air bubbles. So what we normally do, we use a pipette and put few drops of photoresist on top of our wafer. So there may be some air bubble, and because of that our coating may not be even. And usually when we do spin coating, so the, if this is your wafer, the photoresist thickness will have some, this kind of like a profile. So the thickness is little bit more at the edges. So this happens usually, and we have to be careful with this, because that will also change our result little bit. So sometimes if if our process is very critical, and we have like lot of devices, lot of features at the edges also, then we can do like, we can take a little bit bigger substrate, bigger sample, and then we can remove the side part of the photoresist layer using some acetone. So that is what we often do in our lab, so that we get a good thickness, like uniform thickness all over our sample. Okay. And then another problem that may happen during photoresist coating, so the photoresist is a chemical. So many times when we keep this chemical inside our lab, some particle contamination, not exactly contamination, some particle formation happen inside the photoresist. So sometimes people use filters to filter out those particles, because uh, the particles will change our lithography result. Because if say we have like a particle here that will be of some big size, because these are can be of micron size, then we will have our mask, photo mask here on top of it, say some design is there, and we are doing photolithography using this mask, say, then the contact between our photoresist and the mask will not be proper because of this particle. Okay. And with time the photoresist thickness also changes, so whatever we are actually start, like say we started with some thickness, after some time the thickness of the photoresist got changed, because so we are, if we keep the chemicals for a longer time, so the thickness may not be exactly same that we started with. Okay, that will also change our results. So these are the things we have to keep in mind while doing photoresist coating and in general photolithography. So I will write down a few common defects during photoresist coating. So thicker resist layer, at the edges, and there may be air bubble formation. Then maybe particle contamination. So this was the second topic that was discussed in the class in this week, week 10, and the next topic was PECVD. So this was discussed in context with this particular microsensor. So here you can see that we have this SiO2 layer, so we are using it as a mask for during doping as well. So this SiO2 deposition is done using PECVD for the sensor that was discussed. So that is why the PECVD was discussed during the class. So we have already discussed different physical vapor deposition techniques in the live sessions, like thermal evaporation, E-beam evaporation and sputtering, and I have briefly discussed about chemical vapor deposition techniques also. So these are chemical techniques for deposition, so that involves some kind of chemical reaction. So PECVD is one type of a CVD system. If you remember, we discussed about different types of PVD system, can be LPCVD, APCVD, PECVD and MOCVD, etc. So PECVD is what? So plasma enhanced chemical vapor deposition. So in general, what happens in a CVD system, we will have kind of like a tube. So this tube will be of some material that can sustain very high temperature, usually quartz tube, because normally like chemical reaction requires certain thermal energy, and usually like the depositions we do require very high temperature. That is why we need a tube, that is why we need a system that can sustain very high temperature, and there will be thermocouples and heating element connected to this tube, around this tube actually. And then we will place our substrate here, and we will introduce our reactant gas from one window, like from one side, and this flow will be controlled. Might need a carrier gas like argon to like transport this reactant gas towards the substrate where the chemical reaction will happen. And say we introduce the required reactant gas, uh, the like whatever our intended reaction, whatever the chemicals we need for that in a gaseous form, we introduce to the CVD sample, and then the reaction will happen at the substrate, near the substrate, and the byproducts will be removed by the carrier gas, which is usually argon, from outside of the tube. So this is like the basic mechanism of the CVD system. Now, what is the advantage of a PECVD, plasma enhanced chemical vapor deposition? Usually, the CVD systems require very high temperature. So, you know that when we do our processes at very high temperature, that actually increases our thermal budget of our process. So, that is a term, thermal budget is a term associated with microfabrication techniques, and we try to reduce the thermal budget as much as possible, because that actually increases the cost. So we don't want to heat it at a very high temperature, we don't want to do our process at a very high temperature. Also, if we want to make some structure, make some deposition, do some deposition on top of a flexible substrate, which are usually polymer, those substrate cannot sustain very high temperature. For that case also we need some deposition techniques that requires low power, like thermal energy, that can be done at a low temperature, say. So in case of PECVD, so the energy required to for the reaction to happen, that is given by the plasma that is created using a RS source. So this is the diagram of a PECVD system. Say we introduce our gas from one side. So the shower head, aluminum shower head, is for like uniform, like so this reactant gas will uniformly distributed throughout this area because of this shower head, and then RF energy is applied to this electrode. There will be one RF electrode, and that will create plasma which will be near the substrate. Okay, and we keep the substrate on top of a substrate holder, and right now you can see that the temperature is, for this reaction, for this particular diagram, it is given as 280 degrees Celsius, which is actually less if you consider like the typical CVD temperature in APCVD or LPCVD system, because here we are using the energy of plasma for the chemical reaction to happen. Okay, so PCVD is so for SiO2 deposition, PCVD is often used. So the precursor gas for SiO2 deposition using PECVD will be there was a video in this week's content about SiO2 deposition in PECVD. Please go through it. So I'm just giving you some points for that. Which is SiH4. So use nitrous oxide or oxygen. So this diagram is for SiO2 deposition itself. So you can see these two gas cylinders are used here. So these are the precursor gas, and then so we introduce our precursor gas first, and then we create plasma to activate or to start the chemical reaction. Okay, and then full formation. If you remember, we have discussed about SiO2 deposition using sputtering as well. So in our lab we have a SiO2 target in our sputtering system for deposition of SiO2. So SiO2 is a dielectric, so it is difficult to it is difficult to deposit, and when we try to deposit, the deposition rate is less. So that is why usually CVD systems, CVD technique is used for SiO2 deposition or SiO2 formation, or if we are using silicon, we can go for growth. So remember I discussed about different these two terms, deposition and growth. Deposition is like we do some deposition like film coating using some target, whereas growth is we will use some part of the wafer. In case of SiO2 growth, we will use some portion of silicon wafer itself for the growth of SiO2. Okay, so whether we can go for growth, and if we are using a different say substrate, not silicon, then we can go for SiO2 deposition using either sputtering or using the CVD. And PSCVD can be used for flexible substrates or the substrate which cannot sustain very high temperature. So these are the advantages of PECVD. So yes.
Which one will provide thinner, like thin film? How to remember and
Thinner film, so you have to control the deposition rate by controlling the deposition condition. So in case of sputtering, what we do, we control the argon flow rate, we control the power, and that's how we control the deposition rate. And in case of here also, we will not introduce randomly this gas, we will flow it through some mass flow controller and in a controlled manner. So whatever technique you are using, you should know the deposition rate, and at the end of the day you want some controllable rate, right? So I don't remember which will provide like thicker SiO2 film, but as from my experience, I can see that in sputtering it is the deposition rate for SiO2 is lower. I have not used PECVD, like what kind of deposition rate it can achieve actually, but in general, in we have a LPCVD system, not never tried SiO2 growth there, but for other material it gives good deposition rate compared to like sputtering. And in sputtering also, for other material we get like good deposition rate. However, for SiO2, because it's a dielectric, we don't get a very good deposition rate. It's kind of like it gives us thinner SiO2 layer. Of course, we can increase the time, we can increase the RF power, and that will give us a better deposition rate or faster deposition rate, that will give us the thicker film. Okay. So this is like a two different setup. We cannot directly compare that for this amount of time we are getting this thickness. You will compromise with the quality of SiO2. Say if you remember wet oxidation, dry oxidation, wet oxidation gives faster, but the quality is not that good. Did I answer your question, or if you need more?
no, what I'm asking how to remember, like if in exam they will ask which one provide, means which is the best for thin film. So how to remember? Because every time I will be get confused with this.
There is, I don't think that there is something called the best technique for deposition, because it depends on for what purpose you are using. See, ideally we want a good deposition rate, like faster deposition rate. But if you are doing it very fast, say in case of sputtering, we are applying a lot of RF power, and we are providing argon gas in such a way that our rate is high. That will not lead to a very good quality film. There will be lot of defects. So a controllable slow rate will always give a better quality film. And also we know that in case of like physical vapor deposition technique, compared to CVD, the step coverage is always like it's not good. Say if you are using evaporation, if you have a structured film, your film deposition will be something like this. whereas in case of chemical techniques, you will be able to achieve more or less good step coverage. So these are the things we have to consider. One more thing also, like the cost of the technique. Okay, thermal evaporation, the cost is less compared to e-beam evaporation, but then again we cannot go for thermal evaporation. Like for certain material we have to go for e-beam evaporation. So there is like pros and cons for like every processes. The main advantage of PECVD is that it's a low temperature process, and we can go for flexible substrate because it's a low temperature process.
Okay, ma'am.
So I will write down few advantages of PECVD as well. So you will find a comparison between different CVDs like APCVD, LPCVD and PECVD. I request you to go through all this like the comparison, like advantages and disadvantages of this different techniques, because all of these has certain advantages and some disadvantages. And PECVD is definitely expensive one compared, if you compare with APCVD or LPCVD. Low temperature deposition. Next is good film uniformity. And step coverage. Okay. There may be few more advantages as well as disadvantages. You can look for that. So I hope there is no question. I can go to the next topic. So this photoresist coating and PECVD I discussed, keeping this micro cantilever based sensor for breast cancer analysis in mind. So these are the techniques, so these are the like components in the fabrication of the sensor. Okay, and next topic was again like how we can detect breast cancer and cancerous tissue. That is based on the electrical properties of the tissue, and for that we will need a interdisciplinary electrode and some kind of mechanism to measure impedance of the tissue. Okay, so I hope that you have already gone through the video, like how we can fabricate and use this kind of sensor for cancer analysis, cancer detection. So this figure I have taken from the lecture notes. So the sensor is, so this is the impedance sensor, right? So the how they have made the sensor. So first they have used a glass substrate here, and they are making this electrode, interdigital electrode on top of the on top of this glass substrate. And for that they are using gold as the electrode material and a thin layer of chromium for adhesion. Okay, so this is the first deposition the metal, and then they did photolithography, and then the patterning. So this is the first step of photolithography. Now we got the interdisciplinary electrode, then we will make the SU8 well. Okay, this is to hold the tissue on top of the sensor. Okay, so SU8 is biocompatible, so for that they have coated this using SU8. So we know that SU8 is a negative photoresist. It's a polymer, and it is transparent. Like it's a very thin polymer. The like viscosity is such that we can get a very thin layer of SU8 as well. For this work, they are using 7 micrometer thick SU8. So this is a relatively thick. Like we normally don't use this kind of thickness for photolithography. Because they are using it in this sensor as a well to hold a biological sample. That is why they are keeping this thickness as 7 micrometers. I'm sure they have optimized this values. So they need this much of thickness for the sensor to work properly. And after that, they did a lithography, and then they made this pattern SU8. Now SU8, so to achieve this kind of a pattern of SU8, we know that SU8 is negative photoresist. So what kind of mask we need? So what happens in negative photoresist? The exposed area will become hard. Okay. So the mask will be something like this. So so this is our like glass substrate, and then we will have this portion transparent so that light can pass, because ultimately we want this SU8 to remain here. This portion will be opaque, so there will be like chrome coated here in this portion, and then again this portion will be transparent, and this portion will be again chrome coated. So the mask will be like this. So instead of that, if it is a positive photoresist, we are not using a positive photoresist for this purpose, but if we want to make this kind of structure using a positive photoresist, then we will use a opposite mask. So the opposite means the transparent portion will be opaque in that case, and the opaque portion will be transparent. Okay. So it is important to use the correct mask so that we get the final pattern as desired. And one more thing, so you have learned about bright field mask and dark field mask. So bright field mask, most portion will be bright. Say we have a cross here, so this kind of mask will be a bright field mask. Most portion will be bright, and dark field mask will be opposite of this. So this portion will be dark. Now we always try to use this kind of a mask. The reason is that when we do the alignment, so here you can see we have to align this mask with our first photoresist or first pattern layer. Okay. Now we want a mask through which we can see most portion uh, of the sample below that. Okay, this photoresist will be transparent or semi-transparent, so we'll be able to see these patterns from top. Okay, now if our mask is mostly dark, then the alignment will be very difficult. Okay, so we try to select our photoresist, we try to select our mask and design our mask in such a way that our alignment is easy, our life will be easier if we use a bright field mask. So these are some practical considerations that you have to keep in mind while you do photolithography, or if you are going for fabrication. Even if you are not doing by yourself, you are giving your design to someone else to do the lithography. These are the things we have to keep in mind, so that uh, the whole process is easier for like both of you, for the operator as well as for you. So we try to design our mask in this manner. So like the mask designing is one important aspect of photolithography or in microfabrication, and especially when we go for alignment and multiple steps of photolithography. Okay. The next topic was on last two videos were on physical vapor deposition system installation of one system. So if I remember correctly, I have not watched the whole video. The instrument was from HSV in high vac, so I have not gone through the whole video. Please go through it. Like we have similar HSV systems in our lab, so the systems are pretty much similar. So as I mentioned earlier, in physical vapor deposition systems, we will have certain components. Irrespective of the design, we will have certain components. So what are these? So first we will need a water chiller. If you have watched a video, you will know that this is the first component we will need. Because many of these operations, like many of the deposition we will do at high temperature, or there will be like creation of plasma that will also uh, generate a lot of heat inside the system. So we need a water chiller so that our system does not get damaged, and especially say we are using EV evaporators, so we are using high energy electron beam. So in that case also we will need a chiller. So in all the physical vapor deposition systems we have in our lab, we have a water chiller, and that will be there with any system. After that we will also have vacuum pump, because physical vapor depositions we do at relatively not at atmospheric pressure, but will be at lower pressure. Now depending on the type of the system, that will vary, like how much vacuum we need. Thermal evaporation and EV evaporation we do at very high vacuum, but in case of sputtering we initially create vacuum so that there is no contamination, and after that we introduce argon gas that will obviously increase the pressure inside the chamber, but like overall we will need a vacuum system. Okay. Now when we want to go for a very high vacuum, say 10 to the power minus 7 minus 6 millibar, we cannot directly go from atmospheric pressure to this high to this low pressure. We will need two vacuum system. One will create vacuum, so low vacuum, say 10 to the power minus 3. Usually we use a rotary pump for that, and after that we will go for minus 7 or higher than that. And to create very high vacuum we will need different type of pump, diffusion pump or turbo pump. It can be other type of pump, like in case of MV, molecular vapor very the pumps those are used will be different than the ones we normally use. Okay. But the thing you have to remember is that we always need a vacuum pump with physical vapor deposition systems, and if we need very high vacuum for our deposition, we usually use two kinds of pump. One is to create low pressure, and after that we will go for higher vacuum using a different pump. Then if it is like if there, so you know there will be some valves, okay, inside our deposition systems. Now say this is some valve here, so this is initially closed, now we want to open it, something like that. We will have this kind of different valves in our deposition system, in our machine. uh, Sometimes there will be like a physical handle connected to it, we have to move it manually, and most of the time so these are automated, so we'll press a button to close or open any valve. Okay. For that, so we sometimes need an air compressor, because those valves can be pneumatic, so using air pressure these valves will be open or closed. So this is not necessary, but most of the systems have this. Then another important thing is power supply and a control unit. And of course we'll have the main chamber where we will do the deposition and create vacuum. And we might have a load lock chamber. So what is a load lock chamber? Sometimes we don't open our in many systems we don't open our main chamber directly, because if we, so this chamber, the pressure inside during deposition or initially when we are operating, that will be like very low, say 10 to the power 7 millibar. And if we cannot directly open the chamber, we have to vent it slowly, but we don't normally want to vent it directly from very good vacuum. The reason is that after, so say we kept our sample inside the chamber, we load our target, it will take a lot of time to create this high vacuum. Okay, so there will be one load lock chamber connected to it. So if this is the main chamber, there will be a load lock chamber. So this will be connected to a pump separately. Okay, we will load our sample here. Targets we normally place like before it. For target change we obviously have to open the main chamber, but for sample loading and unloading we will use this load lock chamber. We'll place our samples here, and the samples will be moved. So we will create first some vacuum here. This main chamber will be already at very high vacuum, and then we will open this door here and will transfer our sample from this load lock chamber to the main chamber. So this can be manual, so there may be like a arm connected to it. We'll move the arm, or it can be like automated also. We will press some button in the interface, and that will also transfer the samples from the load lock chamber to the main chamber. Okay, so this is not necessary, like in it will not be there in all the systems, but systems those require very high vacuum, very low pressure, usually have this load lock chamber. And also air compressor is also not required if we can like open or close valves manually or in some other way. Okay, so these are the components. Please go through the videos of the installation of the systems. I hope I will be able to identify all of the components and how they work, and basically how we can assemble the systems together for deposition. Okay, so these are the topics those were covered in this week. I will take a pause. If there is any question you can ask, or I will go to the questions. So if there is no question, I will go to the problems. So the first question is, why are nanostructured materials preferred So this is from the last week's constant content, but this is like a very general question, so you'll be able to answer. So why are nanostructured materials preferred in gas sensors over bulk material? Many of you are maybe working in nano and micro sensors. So why what is the reason why we prefer nanostructured materials for gas sensors over bulk material? Not only gas sensors, but in case of, like, in general, case of sensors.
For high surface to volume ratio, ma'am.
Yes.
If you'll use a sensing material in gas sensor, so volume surface to volume ratio will be more.
Hmm. So, like, if our sensing mechanism is based on surface chemistry, some surface reaction, uh, in case of that, so like when we have a sensing material, in case of gas sensors, say, there is this two term, absorption and adsorption, AD and AB. So adsorption is like at the surface, right? So there may be some reaction happen at the surface, and because of that some property of the sensing material may change, and that sense the change may be, say, resistance change or some other property change, and we will be able to, so we will measure that change using so if it is a electrical sensor, then we will measure the change in resistance or the change in voltage or the change in current. uh, Now, for this reaction to happen, this kind of reaction to happen, if it's a surface reaction, we need a large surface to volume ratio. So in that case, we will use a nanostructured material, because we know that in case of nanostructured materials, the surface to volume ratio is high, as you have mentioned. Okay, so that is one advantage. So there will be more reaction sites for the reactions to happen, for the gas molecules to interact. So one exercise we used to do when we studied nanomaterials and nanochemistry, like we can take like a 1 centimeter cube, and we can calculate the surface to volume ratio, and then we can divide it into, say, 4 components and then 8, and then we can calculate the surface to volume ratio, and it will increase as we divide our this cube to smaller and smaller sizes. The surface to volume ratio increase. So we can do this calculation like very easily. Okay, that improves when we have a good surface to volume ratio and more reaction sites for the gas molecules to interact. That will improve the sensitivity of the sensor, that will also improve the response time of our sensor. Also, like nanostructured materials, uh, because of the enhanced surface reaction, because of the surface chemistry, it can provide a lower operating temperature compared to bulk material, and so these are the advantages of nanostructured material over bulk material when we are considering it for sensors. Okay, so I'll write down it. active sites, this improves sensitivity, response time, and reduce operating temperature. Because it depends on the type of the reaction, it may reduce the operating temperature. Okay, so this is the first question. Let's go to the next question. So this is related to breast cancer analysis. I will give you few like two statements. Tell me like whether the statements are true or false. You can write in the chat box. Identify whether the, let me write down the question first. Following statements first is mammography is less effective in dense breast tissue increasing the risk of false negative. The second statement is I will take a pause. You can give me the answer. So this course is on sensors and actuators, but many of the sensors that we have discussed are biological sensors. So that is why I have included these questions, because in like earlier weeks also we have discussed about cancer cell detection and other biosensors like don't remember, mainly related to cancer detection. So we have discussed this. both are true. Yes. So both statements are true. So mammography, this is a X-ray imaging technique. So X-ray imaging is done to find if there is some abnormal mass or tumor. So this is not effective for dense breast tissue. Okay, that can result false negative. And the statement that some biocancers, breast cancers, do not have the common biomarkers. We have three common biomarkers. Presence of this three will give an indication that the tissue is cancerous, but in many cases, so the some breast cancer cases are triple negative breast cancer. uh, like any of and no none of these biomarkers are present, but still the tissue can be cancerous. For that, we need further analysis. So overall, this kind of technique, the further analysis and other additional methods of detection, those will increase the diagnosis time, and that is where actually many people are like trying to make sensors for a non-invasive and easy detection of breast cancer to actually reduce the diagnosis time. uh, Again, remember, these techniques are often used along with the conventional techniques to improve the accuracy of the conventional techniques, not a standalone or gold standard method. Because many times, say we are measuring the electrical properties of a tissue, uh, the change in the electrical properties may not be a result of the cancerous tissue. It can be a result of some other kind of disease, some other kind of abnormality. So that is why we have to use a common and conventional analysis techniques. But overall, the set of like this diagnosis techniques that improves the accuracy and reduces the diagnosis time. So you can like search for what other conventional techniques are used for breast cancer analysis, and what are the disadvantages and advantages of it, and why we are actually working in, like why many research groups are working in like for fabrication and designing of microsensors for cancer cell detection. Okay, so like it's before working in an area, it is also important to know the advantages and disadvantages of already existing techniques. What are the costs associated with it, and what is the expected time required for that. So many of the techniques, so this is like biopsy, so this is an invasive technique. Some tissue will be required, so lab testing will be required. Some professional technician will do the experiment. uh, the person and that lab setup will be required for certain kind of disease detection. But like when we go for sensors, we can make the sensor interface in such a way that uh, the detectable signal that can be like in a readable format to a common user. Okay, maybe like a binary, like yes no kind of, like yes no, green red kind of signal, or it can be a quantitative signal. Say like if the range, say suppose we have certain chemical in our body that should not be there inside, and there is like safe level, there is this risky level, and this is dangerous level. See, we can make a sensor to show this, indicating if it's a green or it's a yellow or a red. That in the red indicates the level is dangerous, so you can make a sensor that is readable for common like human being, rather than uh, going for a lab test. Okay, so in that case, that will actually reduce the diagnosis time, and people can react, and people will have more time for treatment. These are the main reasons why many research groups are working in sensors, especially in case of biosensors and biological sensors for disease detection, mainly for disease detection, so that overall we can improve, either it can improve the accuracy or reduce the diagnosis time. Also, you can look for what are the three biomarkers for breast cancer. Okay, I have not included it, you can look for it. You can write a few in the chat box, or you can unmute and speak also. What are the some advantages of piezoresistive MEMS sensor? You can write the advantages, particularly for like say disease detection, cancer cell detection, based like compared to other techniques. Trying to highly sensitive, work at low temperature, so low power consumption. Yes, low power consumption and good sensitivity is the advantages of any MEMS based sensor, because these are very small dimension sensors, so they don't require a lot of power. Response time is high. High, that should not be an advantage, right? High response time. Compact, yes. Fast, yeah. That will be definitely faster than going for some lab testing. May not be exactly accurate, but some quick detection it can give. So I will write the advantages, mainly considering this breast cancer analysis, that in mind. Okay, one technique can be, it is non-invasive. So biopsy, which is an invasive technique, if we can make a MEM sensor, piezoresistive based MEM sensor, that can be directly used. We can make a sensor which is non-invasive. So this is always an advantage and less uh, difficult for the patient. Okay, can be non-invasive, can be invasive as well, depending on the design and the type of the sensor. Another advantage is the high sensitivity. So this is mainly the advantages of any MEM sensor, because these are small sensors. They can provide even a small change. So in a piezoresistive cantilever based sensor that we had discussed at the beginning of the class, so it is a micro cantilever, so even a small change in the elasticity of the tissue, that can be detected as well. Okay, so the sensitivity is usually high. And another advantage is that we can make a small, like you mentioned in the chat box, that we can make a very compact sensor if it is a MEMS based sensor. Okay, so the whole sensor will be portable, whole sensing system can be portable. So we don't need to go for some lab. So this can be true for any other disease detection also, if it is. So in case of cancer cell detection, cancer tissue detection, we definitely cannot rely only on sensors. We have to go for traditional conventional methods. But if for some other diseases, we if we can make a sensor which is portable, small in size, that will be definitely an advantage, rather than going to some cell lab testing facility, and where a trained person will do the testing, and we have to wait for a couple of hours for the results to come. Okay, portable and low cost. If we can make our design in such a way that it is compatible to the already existing fabrication techniques, we can make like large number of sensors in one fabrication in one go. That will reduce the overall cost of one sensor. Also it will be definitely lower cost than like going for a testing in a lab. Okay, in that way MEMS based sensors are low cost. Sorry. Yeah, so these are some advantages of a piezoresistive MEMS sensor. You can think about like you can think of many other advantages as well, and include in your notes. Okay? Mass production is easier, yes. Once we know that, once we finalize our design, we know that our system will work, say in this range of detection, then it's we can go for mass production. Okay, and that will reduce the overall cost. Sensitive to parameter variation, in general MEMS sensors are very sensitive. um, we a small variation can be detected. And also if we are making an electrical sensor, then it is, so we can make interfacing circuit along with it in such a way that overall we can make some interfacing circuit with that, the overall efficiency of our system increases. Okay, so not only the sensor, um, along with that we can make some circuit to improve the efficiency of our system. Ma'am, you are on unmute. If you want to include some point, you can include. So next question I will give, I have just discussed, I have already discussed. uh, Maybe you can try to remember and write down whatever I have discussed in the class. Okay. What is the primary advantage of using PECVD for SiO2 deposition compared to thermal CVD? This is APCVD, like the normal one. The options are
So,
higher deposition temperature, lower deposition temperature, lower cost. So yeah, let's skip these three options. You already know what is the correct answer. You can write it
low
down.
deposition temperature, yeah.
Low deposition temperature is because mm, so in general CVD systems require very high temperature, as I discussed, because the chemical reactions happens at a very high temperature. In case of PECVD, that the energy that is required for the chemical reaction to happen, that is provided by the plasma. So we create plasma using RF's energy source, and that energizes the reactants, gases, and the chemical reaction happens like that. So this is the main advantage of it. The atmospheric pressure CVD or thermal CVD, that is definitely the lower cost one if we think like different types of CVD systems, because in PCVD we should have this arrangement of RF signal, RF generator, and matching circuit, all of those. In case of LPCVD we will need, so in thermal CVD we do the deposition at normal atmospheric pressure. In case of other CVDs we will use a lower pressure, so we'll need a vacuum system for that, maybe not very high vacuum like we have in physical vapor deposition systems. So that will include a cost, and also in case of some other CVDs like MOCVD will use some expensive precursor gases. Like if we compare PCVD and thermal CVDs, the lower deposition temperature is the main advantages of PCVD. So it is suitable for sensitive substrate, flexible substrates. Next question. Why is impedance measurement alone not sufficient for detection of breast cancer? So there I will give you options. There may be like multiple options may be correct. It cannot provide structural details of the tumor. B is it uses harmful radiation. C is other conditions may have similar impedance value which are not cancerous. It is highly accurate can tell me the answer. I will take a pause here.
A and C.
A and C. Yes. Just so the correct answers are A and C. Impedance measurement cannot provide structural details. If we go for imaging, that may give, like say, SEM imaging, that may give some structural details. But if we are using only impedance measurement, then we have to like combine it with other techniques like mammography to get the structural details, the shape and size of the tumor. It uses harmful radiation, so this is not true for impedance measurement, but it is true for mammography. So in case of mammography, X-ray imaging is done. We have already discussed that one disadvantages of mammography is that it is not useful for dense tissue. Another disadvantage is that it uses X-ray radiation, and if multiple uh, diagnosis is done, then that can be harmful for the patient. And yeah, third option is other conditions may have similar impedance value which are not cancerous. So this is true. Um, so, and we have to couple it with other techniques like biopsy for accurate detection. But yes, it can give an initial indication that something is wrong. Whether it is cancerous or not, that's a different concern. But if there is some problem, that can be detected using a impedance sensor. This is highly accurate and can be used alone for diagnosis, so this option is not true. We always couple this kind of measurement along with some conventional techniques, especially when we are doing it for some critical parameter detection, critical disease detection. Then we always try to confirm it using like multiple detection or diagnosis techniques. Okay, so let's go to the next question. Why do most physical vapor deposition systems use two vacuum pump? So what is the answer?
For good adhesion as well as high vacuum is achieved using two pumps.
Yes, for low contamination and good deposition, we need good vacuum in PVD system. Uh, but mainly Priya, you want to add something?
Ma'am, one pump is like for remove air or to remove vacuum, and another one to suck that plate, whatever substrate will be there. I think so.
Okay. So, vacuum systems used in any system, like vacuum pumps used in any systems, those that is like a separate topics in microfabrication, because it is not so if we want to create very good vacuum, it is not easy to create vacuum. So the most common pump we use, that is the rotary pump, that will give some say 10 to the power minus 3 m bar of pressure. And we know that we don't do deposition, especially evaporation, EBM evaporation and thermal evaporation in this pressure. Lower the pressure is always good. For that we need some pump that can create very good vacuum. The cost will be obviously higher, the maintenance will be also high, and for that we use say turbo pump, diffusion pump or cryogenic pump, where see for very good vacuum, if we are making some critical device that needs very like low defects, don't want any defect, otherwise our device performance will be really bad. In that case people use very like a good vacuum pump, and then they try to use instead of a water chiller. This is what my supervisor told me, that when he was doing his PhD and postdoc, they used to cool it using liquid nitrogen, so that the contamination is very low. Okay, the number of particles and device failure is very low. In that case the cost of those kind of pump will be very high. So usually what we do, we open the main chamber, at least if not the main chamber, the load lock chamber. So directly don't use that high like good quality pump that can create very high vacuum directly. Okay, the pumps will get damaged. So what we do, we use two pumps for that. First one will create some low vacuum, and after that we will turn on the second pump that can create very high vacuum. Okay, so this will result that we will achieve very low and high vacuum efficiently, and our pumps will also not get damaged. The load on the pump that is that we use for to create high vacuum, that will be less, and we always create initial low vacuum using a pump like a rotary pump or some mechanical pump, so that uh, we can turn on the vacuum like the high vacuum pump, and that will not damage our system, damage the pumps. So low vacuum is generally achieved using a rotary pump. And for high vacuum, there can be turbo so the working mechanisms are different, how these pumps work. You can use a turbo molecular pump, or a cryogenic pump that will be that will give us a very high vacuum if we require. Cryogenic. Okay. And the cost is obviously higher for the pumps that can create very good vacuum. Okay. Now these are the things we have to keep in mind while operating the systems, because we don't want, so if our system is at atmospheric pressure, we don't want to, first of all, if there is a safety mechanism along with the system, and it is a fairly automated system, then it will not allow to turn on the high vacuum pump, say turbo pump, directly. So there has to be a minimum pressure inside the chamber. After that only the turbo pump can be turned on. Okay, if it is an automated system, there will be some kind of interlock, and if it is a manual system, then we have to be very careful that we don't open the high vacuum pump directly. Like, we have to wait for a sufficiently long time after turning on the first rotary pump, that we have achieved a good level of vacuum, and after that only we will turn on our the main pump. So along the similar line, so this is a very general question. You can think and like give me few answers. So if you have watched the videos, certain precautions while operating the system, while installing a PVD system was discussed. So this is similar to that, like this question is on that, what kind of safety precautions we have to follow if we want to operate a PVD system, say. And you can just think and give me some answer based on your understanding. We have discussed about PVD techniques quite a lot in this course, so you'll be able to give for at least few answers for this. So learning about this topics, like theoretically, that's a different thing, and like when we use it like practically, then we also learn a lot of things, like the safety precautions are necessary while operating a systems, because we are dealing with normally a very high voltage, say very high energy RF signal, or if we are doing sputtering, then this is sputtering, then we do at a very high power, the voltage is in the kilovolt range, so you have to be always careful while operating the systems. So I will wait for some time. I can try. If not, I will write down few. So the list is not limited to like whatever we discussed in the class. Uh, you can add many more to the list. Okay. Okay, I will write down few. We don't have much time. You can think about it and add more to the list what I will give right now. So first thing is that we should use safety goggles wherever necessary, especially when we are using say plasma or laser. Say when we do e-beam evaporation, so when the electron beam hits the target and initial melting is happening, then the brightness of that, because it's in a molten state at a very high temperature, uh, the brightness is so high we cannot see it directly, so we normally use a protective goggles in that case, and it is always a good idea to keep one beside the PVD system so that we can use whenever required. And the next can be vent the chamber properly. Okay, why it is important? We do the PVD physical vapor depositions at a very high vacuum. Okay, and after the deposition is done, first thing is that we have to wait for sufficient duration so that the substrate and the target everything gets like say cool down to a normal temperature, at least below 50 degrees Celsius. Okay, so that we can actually handle our systems. Uh, and the thing is that the inside the chamber the pressure will be so low and we cannot directly just open it. Okay, so we will vent the chamber properly. Usually we supply some nitrogen gas to it that is at a very low say pressure, and we slowly vent the chamber so that there is no damage happens. Okay, so this is very important. When something is at a very high vacuum, we don't open it directly. Next can be electrical safety. As I mentioned that uh, there may be like a very high DC or RS signal, high voltage DC and high power RS signal, so electrical safety is important. And so these are few things. There may be some kind of like vacuum explosion may happen, so we have to be careful. And then there can be some material risk as well. Say we are using some toxic gases for deposition, and we there is some leakage in our system, so that toxic gas will fill the ambient environment and that can cause problems. So these are the things we have to be careful. So leaks are like often, like we have to check for any kind of leaks periodically in a PVD system. So these are the things, these are some safety precautions. As I mentioned, there may be many more to this list. You can think about it and add more to the list. Okay, so it's almost time, so I will wait for some time. If there is any question you can ask, or otherwise I will stop the session here. Oh, so I forgot to check this. Yes, gloves, we have to wear gloves while loading the target, while loading the samples. Yes. Is there any question or doubt? If not, I will stop the session here. Okay, so if no question, then thank you everyone. Thank you for attending the session. I hope that the session was useful. Okay, so uh, we have already done with 10 weeks of live session. We will have 2 more. So see you in the next sessions. Thank you. So I'm leaving this meet.